In 5 seconds, you're going. Okay, well, I think I might start up with our introduction here today. So anyway, for those of you who don't know me, I'm George McKee from the University of Wisconsin, and I'll be chairing today's Southern California UC D3D seminar. And we're very happy to have Emily Belli from General Atomics giving a very exciting presentation. So typically, plasmas tend to be rather finicky objects, phenomena that we've been striving to understand, and usually nature and plasmas make things difficult on us. But there's one rare thing that has kind of turned out to work in our favor, and this is the so-called isotope effect, in the sense that in general, as ion mass and your ion gyro radius get bigger, a simplistic approach would say that your transport is going to get worse. But magically, plasmas actually show better confinement, which is exciting as we look towards deuterium and DT, ultimately DT plasmas. But understanding why that happens is still a mystery, perhaps until now. And so Emily Belli is going to explain to us some of the underlying physics for this. So Emily, just as a brief introduction, is a research scientist in the Theory and Computational Science Division in the Magnetic Fusion Group at General Atomics. And she received her PhD from Princeton University in the Astrophysical Sciences Department. And since coming to General Atomics, she's focused on development of turbulence models and high performance computing codes to implement these models and calculate transport, both neoclassical and turbulent transport. And actually some of her codes are very well known nationally and internationally. She's the primary developer of the neoclassical code that is used all over to predict neoclassical transport in Tokamaks and related devices, and also a co-developer with Jeff Candy of the C-gyro code, which is also very widely used around the world. And she's also been a leader and executive committee member of many different MFE committees, including the US Burning Plasma Organization, Edge Coordinating Committee, International Sherwood Theory Committee, and as a principal investigator on some edge simulation code grants. So we're very happy to have her presenting today on the topic of understanding the hydrogen isotope effect mystery in tokamaks. So Emily, it's all yours.
Great, thank you, George. So this talk is about developing a theoretical understanding of the scaling of turbulent transport in tokamak plasmas with different isotopes of hydrogen as the fusion fuel ions, and resolving a long-standing mystery known as the isotope effect, where theory and experiment disagree. So for background, so we're all on the same page, it's good to first review exactly what we mean by turbulence and the relation to the global transport and energy confinement. So a power-producing fusion reactor will require very good confinement of the plasma particles and energy such that it can maintain the high densities and temperatures for fusion to occur. And in present-day experiments like the D3D tokamak at General Atomics, reasonably stable plasmas with respect to macroscopic MHD can already be generated with desired current and density profiles. But for the energy confinement, here we show a plot of the measured confinement time of existing machines versus the empirical predictions with a projection to ITER, which is expected to have about a factor of 10 improvement. So the energy confinement time tau E scales roughly as the characteristic length scale of the device squared divided by the thermal diffusivity chi. And thus to lengthen it, we can enlarge the device, though this is economically prohibitive, and ITER will already be about 4 times the size of D3D. For example, you can compare the size of a person, circled in red here, relative to the size of each device, where for ITER, a person is very tiny, or we can reduce the heat transport. So understanding plasma transport is essential to designing a device with optimal confinement properties. So what exactly does transport mean in a tokamak? Well, the fundamental issue is that we desire a hot, dense core, and our solution is to, of course, magnetically confine the plasma in a tokamak. And we know that the tokamak has a helical magnetic field that is toroidal plus poloidal, and the magnetic field lines lie on closed nested surfaces that we call flux surfaces. So the parallel transport along the magnetic field lines is much faster than the radial transport across the flux surfaces, but it is the radial transport that we're interested in since it carries the plasma from the hot core to the cold edge. Thus, to study confinement, we will follow the radial evolution of the plasma density and temperature across the magnetic surfaces, which are defined by simple 1D transport equations, where gamma and Q are the transport coefficients, specifically the particle and energy fluxes, and Sn and St are the particle and heat sources. So transport in a tokamak is generally described by one of two processes. The first is neoclassical or collisional-driven transport, and the second is turbulent transport. And the turbulent transport is generally dominant in a tokamak, so this will be our focus here. And in particular, we will be using gyrokinetic simulations. So the gyrokinetic equation, solved in codes like C-gyro, is the fundamental equation describing microinstability turbulence driven by drift waves. And physically, drift waves are basically ion acoustic waves that are destabilized by inhomogeneities in the plasma. And they are characterized by small amplitude fluctuations in the electric and magnetic fields, delta phi and delta p, low frequencies relative to the cyclotron frequency, and spatially long parallel wavelengths along the magnetic field lines and short perpendicular wavelengths. And these define the gyrokinetic orderings. So the gyrokinetic model allows us to study various classes of pressure gradient driven drift waves. And the ones that we'll be focusing on here are mainly ion and electron temperature gradient driven modes, ITG and ETG, which are dominantly driven by the ion and electron temperature gradients from the hot core to the cold edge. Trapped electron modes, or TEM, which are primarily driven by density gradients, and electromagnetic driven kinetic ballooning modes. So from our solution of the gyrokinetic equation, we can compute the turbulent transport coefficients like the particle flux gamma and the energy flux Q. So our particular focus here is on the scaling of the gyrokinetic turbulence with different isotopes of hydrogen. And understanding the scaling of plasma turbulence and energy confinement time with hydrogenic isotope mass is an important theoretical challenge for fusion, since most tokamak experiments operate with deuterium as the main ion species, while fusion reactors like ITER will use a 50-50 deuterium-tritium fuel composition to increase the thermonuclear reaction cross-section. In fact, DT tokamak experiments have been done only a few times over the past few decades. The first time was in 1991 at the JET tokamak in the UK using a 90-10 deuterium-tritium fuel mixture, which produced about 2 megawatts of fusion power over a 2-second pulse. 2 years later, a 50-50 DT campaign was run at the TFTR tokamak at PPPL, which in 1994 produced a record of 11 megawatts. This was then eclipsed in 1997 when JET ran its own 50-50 DT campaign, which ultimately produced 16 megawatts, which is still the current record today. But even more importantly, during this campaign, the scientists were able to demonstrate stable, sustained, high confinement mode regimes, for example, by sustaining 4.5 megawatts over a 5-second pulse for 22 megajoules. And since then, over 2 decades have gone by without any DT tokamak experiments until just very recently when JET began its own second 50-50 DT campaign, which is still currently underway. But already in December of 2021, they announced a new record of 59 megajoules. And while these new experiments are giving us a chance to validate our models, the sparsity of the data motivates using theory to help plan for the ramp-up stages in ITER from hydrogen to deuterium to reactor-level DT. So in this work, we develop a theoretical framework for understanding the hydrogenic isotope mass dependence of turbulent plasma transport, which is responsible for most thermal and particle losses in tokamaks. So first, I will give a brief overview of the long-standing discrepancy between experiment and theoretical predictions known as the isotope effect. Then I will provide a theoretical basis for simple gyrokinetic isotope mass scaling of the turbulent energy flux that we will call naive gyroBohm-scaling. Using gyrokinetic turbulence simulations of a DIII-D experiment, I will illustrate an interesting transition in the isotope mass scaling of the turbulent energy flux from ion-dominated core transport regimes to electron-dominated edge transport regimes. The role of the nonadiabatic electron drive in regulating the isotope mass scaling of the turbulence, and in some cases leading to a reversal of naive gyroBohm mass scaling toward agreement with the experimental trend, will be explained with a new analytic scaling law which characterizes the electron-to-ion mass ratio dependence of the flux. I will then discuss the broader implications of these results for the global energy confinement and lowering the power threshold for the low to high confinement or L to H mode transition. And finally, while here I will focus mainly on the energy flux, much of what I will describe also applies to the particle flux, though here the interesting physics occurs for the case of multi-ion plasmas like mixed DT fusion fuel, where I will show that an asymmetry or so-called DT particle flow separation can develop, and I'll discuss the implications of that for the global particle confinement. So I'll begin with the isotope effect. So the scaling of global thermal energy confinement time with hydrogenic isotope mass has been studied in many different experiments, mainly comparing deuterium and hydrogen plasmas. And as shown here, experiments generally find an increase in the confinement time with increasing ion mass, which is favorable comparing hydrogen to deuterium to DT with the coefficient alpha M ranging from 0 to 0.85, depending on the plasma regime and operating conditions. And this favorable scaling contradicts simple theoretical arguments. So dimensional analysis for the ion thermal diffusivity based solely on the ion gyroradius and based solely on the gyrokinetic equation and using the ion gyroradius as the characteristic length scale and the ion thermal speed for diffusive type transport predicts that the turbulent ion energy flux is gyroBohm scaled, where QGBI is the ion gyroBohm factor. So for the rest of this talk, this is what we will call naive gyroBohm-scaling. And in this limit, C0 is mass independent, depending only on parameters such as the density and temperature gradients driving the turbulence. Normalizing by the deuterium gyroBohm energy factor, QGBD, naive gyroBohm-scaling predicts that the turbulent ion energy flux scales as the square root of the ion mass, such that QH is less than QD is less than QDT. This implies that the global energy confinement time degrades with increasing ion mass. Thus, naive gyroBohm-scaling contradicts the experimental trend, and the discrepancy in the ion mass scaling between experiments and theoretical predictions is a long-standing problem known as the isotope effect. So recently, several theoretical mechanisms have been proposed that can lead to a deviation from naive gyroBohm mass scaling of the turbulent ion energy flux. And these include E-Crosby flow shear, electromagnetic fluctuations, collisions, impurities, fast ions, and kinetic electrons. However, most previous work has focused on the core region, and as such, a reversal of the scaling, that is ion flux decreasing with increasing ion mass toward agreement with the experimental trend, has been demonstrated for only limited cases. So in this work, we present a theoretical framework for the role of the non-adiabatic electron drive in the isotopic dependence of turbulent transport and the mechanism by which it can lead to a transition from gyroBohm-like scaling in the core to a strong reversal in Elmwood edge regimes. The overall idea is that while naive gyroBohm mass scaling is based on the physically unrealistic assumption of adiabatic electrons, when kinetic electron dynamics are properly retained in the gyrokinetic analysis, we expect a more complicated scaling where C0 gains additional dependence on the electron-to-ion mass ratio. The ion mass dependence of C0 typically opposes the baseline gyroBohm ion mass dependence of QGBI, and as we will show, can in some cases dominate and reverse the gyroBohm ion mass scaling such that QH is greater than QD is greater than QDT. So I will first illustrate the reversal of naive gyroBohm mass scaling of the energy flux in the edge numerically with nonlinear gyrokinetic simulations. So to establish an experimentally credible baseline scenario for our isotope studies, we consider a D3D ohmically heated L-mode deuterium experiment. And gyrokinetic turbulence simulations are carried out with the CGyro code. So for verification, we first show that CGyro matches the total deuterium plus electron experimental power balance energy flux spanning a broad radial range from the core region where ion temperature gradient driven or ITG turbulence dominates to the edge region where trapped electron mode or TEM turbulence dominates. So in the Elmwood edge, the turbulent transport becomes explosive due to parameters that enhance the non-adiabatic electron drive. Dominantly large safety factor Q, but also large electron temperature and density gradients such that the electron energy transport is comparable to or larger than the ion transport. For isotope studies, we compare the simulated deuterium ion energy flux against hydrogen and against DT with all other experimental profile parameters fixed. For all three species, the ion flux increases significantly from the core to the edge, but the mass scaling in the two regions is different. In the core, a naive gyroBohm-like mass scaling is observed, with ion flux increasing with increasing ion mass, while in the edge, a reversal from naive scaling is found with QH greater than QD greater than QDT, which implies that the hydrogen confinement relative to deuterium is significantly worse than expected by the naive scaling, while the DT scaling is better than expected. The significant increases in the nonlinear fluxes from the core to the edge is consistent with the increase in the linear growth rate of the dominant drift mode. But comparing the three species, the linear growth rate follows the intrinsic mass scaling in both regions. So in the zero electron mass limit, the linear growth rate gamma scales as the driving gradient term omega star, and thus as the inverse square root of the ion mass, such that in absolute units, gamma decreases with increasing ion mass, as we see here. Intrinsic mass scaling then implies that gamma is independent of the ion mass when normalized by the main ion thermal timescale, A over V thermal I, such that the HD and DT curves on the right-hand side plot should be exactly the same. However, because kinetic electron dynamics are included in the simulations, a slight deviation from the intrinsic scaling is seen in the edge, which increases as the ion mass decreases as the electrons become more non-adiabatic. A mixing length estimate for the ion thermal diffusivity based on the linear growth rate then follows the trend of naive gyroBohm-scaling with the square root of the ion mass scaling, with chi increasing with increasing ion mass. Thus, while mixing length theory predicts the increase in transport from the core to the edge, it is not able to capture the reversal in the ion mass scaling. So in what follows, I will show that the favorable reversal in the isotope scaling of the turbulent energy flux from the core to the edge arises from finite electron mass corrections. So the finite electron mass dependence that gives rise to breaking of naive gyroBohm mass scaling of the turbulent energy fluxes and intrinsic mass scaling of the linear growth rate enters through 5 physically distinct effects: electron-ion collisions, plasma rotation, electromagnetic fluctuations, finite electron Larmor radius, and the electron parallel motion. For the first 3, the apparent dependence on the electron-to-ion mass ratio is effectively reducible by rescaling with respect to the main ion thermal timescale, while the latter 2 are irreducible. So to see this, here we show the simulated turbulent ion energy flux versus electron collision rate nu-e in fixed units. So importantly, here the fluxes are normalized by the main ion gyroBohm factor, QGBI, rather than by fixed deuterium gyroBohm units. So recall that naive gyroBohm-scaling implies that the HD and DT fluxes should be exactly the same in these main ion units, since C0 is a constant independent of the ion mass. Here we find for all 3 species, the ion flux decreases with increasing nu-e. So the main effect of collisions on drift waves is that pitch angle scattering collisions detrap trapped electrons. And this is shown here illustratively in pitch angle C versus theta phase space diagrams of the electron distribution function, where closed contours are trapped particle orbits and open contours are passing orbits. So the effect of the collisions is basically to break apart the trapped passing particle boundary, thereby reducing the effective trapped electron fraction and reducing the ITG and TEM linear drives. However, here we further find that lighter isotopes are more weakly stabilized by the collisions. So as noted first by Nakata, this is consistent with the fact that the ratio of the electron collision rate to the ion transit frequency scales as the square root of the ion mass, and thus the collisions are less effective at stabilizing the turbulence drive as the ion mass decreases from DT to D to H, as we see here. So we will refer to this as the fixed collisions effect. However, the apparent mass dependence from collisions can mostly be eliminated by rescaling the electron collision rate with respect to the main ion thermal timescale A over V thermal I, as shown on the right plot. And this essentially shifts the hydrogen and the DT curves by the square root of the ion mass, and naive gyroBohm mass scaling is again recovered. A similar effect can be shown for rotation. So toroidal rotation arises in tokamaks from external torque due to neutral beam injection for plasma heating. And the induced E cross B flow is believed to play an important role in the suppression of turbulence. So here we show the simulated turbulent ion energy flux versus rotation E cross B shearing rate in fixed units. And for all three species, the ion flux decreases as gamma E increases, as the perpendicular flow shear can tear apart turbulent eddies through nonlinear decorrelation, as shown here illustratively on the right, comparing simulations without and with gamma E. However, here we further find that lighter isotopes are more weakly stabilized by the E cross B flow shear, such that naive gyroBohm-scaling is strongly broken, comparing DT to D to H at moderate to high gamma E. So as noted by Garcia, this is consistent with the fact that the ratio of the E cross B shearing rate to the ITG linear growth rate scales as the fixed external rotation rate, omega 0, over the ion thermal speed, and thus as the square root of the ion mass. And this indicates that the effectiveness of the E cross B flow shear for quenching the turbulence decreases as the ion mass decreases from DT to D to H, as we see here. So we will refer to this as the fixed rotation effect. However, as with collisions, the apparent mass dependence from rotation can be eliminated by rescaling the E cross B rotation rate with respect to the main ion thermal timescale A over V thermal I, as shown in the right plot, and naive gyroBohm mass scaling is again recovered. So for our D3D case, in both the core on the left and in the edge on the right, the effect of keeping the collisions and rotation fixed in absolute units, rather than rescaling with respect to the main ion species, stabilizes the DT turbulence and destabilizes the hydrogen turbulence, as indicated by the change in the fluxes from the blue to the yellow bars. However, because the effects are relatively weak, the overall trend of the mass scaling in each region, whether gyroBohm-like in the core or reversed in the edge, is preserved. Aside from collisions and rotation, for our particular D3D case, electromagnetic fluctuations and finite electron Larmor radius effects are negligible and do not play a critical role in the isotope mass scaling. Our focus then will be on the finite electron mass dependence from the irreducible electron parallel motion. So a new isotope mass scaling law has been developed to describe the electron-to-ion mass ratio dependence of the turbulent energy flux that arises from the non-adiabatic response associated with the fast electron parallel motion. So we write the ion and electron gyrokinetic equations in dimensionless form, where time is normalized by the main ion thermal timescale. So here, Hi and He are the ion and electron non-adiabatic distributions. The U parallel term is the parallel streaming along the magnetic field lines, and the right-hand side terms Gi and Ge represent the totality of the remaining terms in the equations, which depend on a vector of dimensionless parameters P, containing geometry quantities, profile gradients, E cross B rotation, and collisions, all of which are considered to be fixed or independent of the electron-to-ion mass ratio. So when writing the equations in this form, there is only a single irreducible term that can be responsible for the ion mass dependence of Qi over QGBi, the electron parallel streaming. In the zero electron mass limit, the solution of these equations is the balanced average distribution HEB. The balanced average distribution is associated with trapped electrons only and is independent of the electron-to-ion mass ratio and gives rise to naive gyroBohm-scaling of the flux. Corrections to this limit are obtained by expanding the non-adiabatic part of the electron distribution as an asymptotic series in omega over the electron bounce frequency omega BE. Thus, we introduce the related but explicit ordering parameter epsilon, which contains the parallel connection length QR and the electron-to-ion mass ratio. So the finite electron mass non-adiabatic correction terms, He1 and He2, contain both trapped and passing electron contributions. The series for the turbulent ion energy flux then becomes as follows, where the coefficients C depend on all system parameters P except the electron-to-ion mass ratio. So the ion mass dependence is always monotonically increasing, meaning that C0, C1, and C2 are positive. So physically, the first term is the naive gyroBohm term, which, as I mentioned, is the solution in the zero electron mass limit, and it scales as the square root of the ion mass. The next two terms are the finite electron mass non-adiabatic corrections, which destabilize the turbulence. The second term is what we will call the weak non-adiabatic term, and note that it scales with the electron mass, but is independent of the ion mass. So it can increase the flux by a constant amount that does not depend on MI. This means that while it breaks naive gyroBohm mass scaling, it cannot produce a reversal. The last term is what we will call the strong non-adiabatic term, and it scales as the inverse square root of the ion mass. And this term is mostly illustrative, as we expect the asymptotic series to diverge in the strong non-adiabatic regime. But nevertheless, it illustrates that reversal from naive gyroBohm ion mass scaling, or ion flux decreasing with increasing ion mass, can occur when the finite electron-to-ion mass ratio corrections from the strong non-adiabatic term dominate. To explore the validity of the new isotope mass scaling law, we introduce a fictitious scaling parameter lambda to the parallel motion in the electron gyrokinetic equation. By adjusting lambda, we can control the size of the non-adiabatic correction by effectively varying the electron response time. So increasing lambda is like increasing the electron mass in the parallel motion only, which increases the effective parallel electron response time relative to the ion drift timescale, making the electrons more non-adiabatic. Higher safety factor and lighter ion species are also more non-adiabatic. So to verify the key role of the finite electron mass, here we show that by shortening the parallel electron response time in the hydrogen simulations by lambda equals the square root of mh over md, so that it is the same as for the deuterium simulations, removes the reversal and yields fluxes which are nearly exactly gyroBohm scaled with respect to the deuterium fluxes, as indicated by the match between the red and the purple curves. We can also explore the explicit role of zonal flows. So zonal flows corresponding to toroidal mode number n equals 0 are turbulence-driven E cross B sheared flows that are generated by the poloidally and toroidally symmetric fluctuations in the electric potential. And they are believed to play an important role in regulating the drift wave turbulence. So here by the orange stars, we show that by omitting lambda from the zonal n equals 0 electron equation, so that it applies only to the finite n non-zonal modes, makes no significant difference to the modified simulated hydrogen simulations. And this indicates that the mass scaling is controlled by the non-zonal parallel electron motion. Or in other words, that zonal flows do not play a significant role in the mass scaling behavior or the transition from naive scaling to strong non-adiabatic. So to further verify this, here we show the ratio of the nonlinear RMS averaged non-zonal fluctuating potential summed over toroidal mode number n to the n equals 0 zonal flow potential for our radial profile scan. And while the ratio varies with driving parameters, it is nearly independent of the ion mass and both the gyroBohm-like and reversed regions. That is, the relative strength of the zonal flows does not change in the transition to the reversed regime, as the zonal flows are simply driven by the fluctuating perturbations whose intensity carries the ion mass scaling. To explore the validity of our new isotope mass scaling law for our D3D Elmwood edge parameters, here we show the variation of the simulated turbulent ion energy flux versus our scaling parameter lambda. The vertical axis intercepts at lambda equals 0 correspond to the naive gyroBohm limit obtained at 0 electron mass, with the ion flux increasing with increasing ion mass. As lambda increases, the linear scaling with the square root of the electron mass predicted by the weak non-adiabatic term is seen, which increases the flux by a constant amount that does not depend on MI. That is, the D and the H curves have the same slope. Finally, as lambda increases further, the increase in the flux becomes stronger than linear, and the scaling enters the strong non-adiabatic regime, where the predicted reversal from naive gyroBohm mass scaling, or QH greater than QD, occurs. So while the previous plot was done in the weakly collisional limit, the scaling trends are preserved even as the collision frequency increases significantly to the experimental level, but become more difficult to measure as the naive gyroBohm coefficient C0 and the weak non-adiabatic coefficient C1 are significantly reduced as collisions rapidly stabilize the TEM drive. But nevertheless, even at high collisionality, the relative flux enhancements in the strong non-adiabatic regime are not reduced. And this is the regime where the experimental edge parameters at lambda equals 1 reside. So overall, in the Elmwood edge, the non-adiabatic electron drive is significantly enhanced by increased Q, such that it not only regulates the turbulence, leading to explosive values of the fluxes, but the associated finite electron mass corrections also dominate the ion mass scaling and play a key role in reversing naive gyroBohm mass scaling. In contrast, in the core, the finite electron mass corrections are weak as Q is low and the driving gradients are small. Here, the non-adiabatic contribution is dominated by the weak term, and despite the small correction to the naive gyroBohm limit, the fluxes are relatively low, and it is still observed that the ion flux increases with increasing ion mass, such that QH is less than QD. Thus, a reversal of naive gyroBohm mass scaling due to the non-adiabatic electron drive is generally not expected in the ITG core, unlike in the edge, unless parameters like the safety factor are significantly increased to increase the effective parallel electron response time to push the solution into the strong non-adiabatic regime. So we can now explore the implications of our new analytic isotope scaling law for the global energy confinement. So here we have considered only the isotope mass scaling of the local gyrokinetic turbulence. To assess the impact on the global transport, a full transport analysis would be needed to evolve the global density and temperature profiles. And one caveat for transport modeling is that this work implies that reduced models of transport, particularly with simplified electron physics, like commonly used fluid or bounced averaged electron models, may not properly capture the finite electron mass corrections to the isotope scaling of the turbulent flux and may need to be reassessed. In addition, influences unrelated to the ion mass and beyond the scope of this work should be considered. And this includes effects like impurities, heating, MHD activity, etc. Nevertheless, considering the important role that edge conditions play in plasma confinement, the favorable reversal in the turbulent isotope scaling of the flux from H to D to DT from the core to the edge shown in this work has implications for trending the theoretical prediction of the isotope scaling of the global energy confinement time toward agreement with experimental trends, and also for lowering the power threshold for the low to high confinement or L to H mode transition. And both of these are consistent with recent experimental observations, such as shown here for JET, comparing deuterium and hydrogen plasmas, where there's an increase in tau E and a decrease in PLH. So we could also consider the isotope mass scaling in the H mode pedestal. And this is a difficult problem due to computational limitations and has not been well studied. However, we can speculate that the isotope scaling in the pedestal is likely driven by several influences, including ion and electron scale turbulent transport and neoclassical transport. So for the ion scale transport, the E cross B shear will likely play a dominant role. And our previous results, consistent with the work of Garcia, showed that for fixed rotation between isotope experiments, lighter isotopes are more weakly stabilized by the E cross B flow shear, and this can lead to a favorable reversal in the isotope scaling of the energy flux. But the electron scale transport is also likely to play a role. For example, recent nonlinear C-gyro simulations of a D3D ITER baseline H-mode case in the pedestal finds that the experiment lies in a bifurcation region between ITG turbulence and ETG turbulence. So shown here are the multi-scale density fluctuations for both the ETG and ITG, along with the wave number spectra, which incorporates both ion scales with K theta rho I on the order of 1, shown in red, and electron scales with K theta rho E on the order of 1, or equivalently K theta rho I on the order of 10, shown here in blue, where the turbulent spectrum peaks. So typical ion scale simulations would include only the wave number spectrum given here in red. But overall, the isotope mass scaling of such multi-scale turbulence regimes, including the role of the electron scale transport and the zonal flows on the ion and electron scale coupling, is not yet known. But we do know that the neoclassical transport might be important. So for example, for this case, in order to match the experimental power balance for the total flux requires not only the multi-scale turbulent transport from the C-gyro code, but also the neoclassical transport from the NEO code, which provides about 25% of the total flux. So to lowest order, the neoclassical ion energy flux scales as the ion gyroBohm factor times the ion-ion collision rate, such that for fixed collisions between isotope experiments, Qi neo scales as the square root of the ion mass with a gyroBohm-like scaling such that QH is less than QD is less than QDT. But overall, the interplay between the ion and electron scale turbulence, the neoclassical transport, and other influences on the isotope mass scaling in the H-mode pedestal is a topic of ongoing research. So I'm now going to shift focus a little bit and talk about the particle transport. So theoretical studies of the turbulent isotope scaling have primarily historically focused on the energy transport and for a single bulk ion species. But understanding the scaling of the particle transport, particularly for multi-ion plasmas like mixed-DT fusion fuel, is also important for a reactor. So while the turbulent radial energy flux in a tokamak is generally positive or outward directed from the core to the wall, consistent with monotonically decreasing temperature profiles, the turbulent radial particle flux can be positive or negative, depending on influences such as turbulence drive, like ITG versus TEM, collisions, which can enhance the inward particle pinch, and E-cross-B shear, which can decrease the particle pinch. Furthermore, while the turbulent energy flux in a tokamak generally says that the ion and electron particle energy fluxes can be quite different, even for a pure plasma, the particle fluxes are constrained by the ambipolarity condition such that the charge weighted sum of the ion fluxes must equal the electron flux. But in a multi-ion plasma, the ion particle fluxes themselves can differ while still maintaining ambipolarity. So here we will explore possible asymmetries in the deuterium and tritium turbulent particle flows. So for these studies, we will use typical core parameters based on the GA standard case and consider 3 different values of the density gradient scaling corresponding to an ITG negative case where gamma is inward or less than 0, an ITG positive case where gamma is outward or greater than 0, and a TEM case at very large density gradient. So for the ITG cases, the ion energy flux is larger than the electron energy flux, and the particle fluxes are relatively low. While in contrast, for the TEM case, the electron energy flux is larger than the ion energy flux, which is consistent with our strong non-adiabatic regime. And correspondingly, the particle fluxes are very large and positive, indicating an unfavorable outward flow of particles from the core. So in steady state, the transport equations require that the particle fluxes from turbulence and neoclassical transport balance the particle sources. Thus, regimes of low particle flux, like our ITG cases, might be expected in the core with low particle fueling, while regimes of larger particle flux, like our TEM case, might be expected in the core or edge with pellet fueling or in the edge due to a wall source. So here, for all 3 cases, we show the variation of the particle flux with ion density fraction ranging from pure deuterium on the left limit of the plots to 50-50 dt at the dotted vertical lines to pure tritium on the right limit. So for all 3 cases, at a given ion density fraction, the deuterium particle flux in red and the tritium particle flux in blue are centered about 1/2 gamma E. And for all 3 cases, we find an interesting observation, which is that at 50-50 dt, the dotted vertical line, there's an asymmetry between the deuterium and tritium fluxes, such that the deuterium particle flux is more positive than the tritium particle flux, indicating that the tritium is better confined than the deuterium. And this observation implies that a plasma with initially equal D and T concentrations will experience so-called flow separation, whereby the concentration will evolve to an unequal state. And the buildup of one species relative to the other could potentially result in a loss of fusion performance. So we can derive an analytic quasi-linear theory for the ion particle fluxes for general electron dynamics that predicts this asymmetry. So I won't go through the derivation here, but rather just show the final result for the ion particle flux that we write in terms of the general electron particle flux and a very complicated factor, delta K, that depends on the fluctuating potential delta phi, the linear growth rate gamma, and the electron temperature gradient scale length A over LTE. The important point is that delta K is order K theta rho squared relative to the electron particle flux and arises from ion finite Larmor radius effects. Furthermore, since delta K is independent of the ion species and is positive for positive temperature gradient scale lengths, the result implies that at 50-50 dt, not only is there an asymmetry between the deuterium and tritium particle fluxes, but also that for arbitrary turbulence regimes, gamma D is more positive than gamma T, indicating that the tritium is better confined. Generalizing for arbitrary ion density fraction, we further find that equal D and T particle fluxes can be restored with a small order K theta rho squared given by the delta K factor deviation from 50-50, and furthermore that the conditions will depend on the electron dynamics. And this in fact agrees with our gyrokinetic turbulence simulations. So for the ITG negative case, where gamma E is inward or less than 0, equal D and T particle fluxes are restored with a larger concentration of tritium and deuterium and a lower concentration of tritium. In contrast, for the ITG positive case, where gamma E is outward or greater than 0, gamma D equal to gamma T requires ND less than NT. For the TEM case, we note that the ion particle fluxes are nearly exactly linear with the ion density fraction, and the asymmetry at 50-50 is very small. And this is consistent with our analytic theory, which predicts that the asymmetry decreases as the electron particle flux increases, such that it becomes insignificant in the strong non-adiabatic regime. But nevertheless, since gamma E is still greater than 0, like our ITG positive case, the shift towards a trend of ND less than NT is still observed to restore the equal fluxes. We can also find that equal D and T particle fluxes could instead be restored by a change in the density gradient scale lengths from the electron density gradient, again by our delta K factor or order K theta rho squared. And in each case, this is specifically by flattening the deuterium density gradient or lowering A over LND while simultaneously steepening the tritium density gradient or increasing A over LNT while still preserving quasi-neutrality. So what is the meaning of these results? Well, the importance of these results is the implications for developing practical solutions for DT isotope ratio control scenarios. So like with the energy flux, here we have considered only a local gyrokinetic analysis. And to assess the impact on the global particle confinement, a full transport analysis would be needed to evolve the global density profiles by balancing the particle fluxes from turbulence and neoclassical transport with the particle sources, for example, including the fueling from NBI heating sources. And this is being done with integrated modeling frameworks like JETO-QualiKIS. But control scenarios may ultimately involve core or edge pellet fueling or edge gas fueling for the mitigation of ELMs. And these studies are being done experimentally, currently in connection with the JET-DTE-2 experimental campaign. For example, in preliminary results, by injecting deuterium pellets into a primarily gas-puffed hydrogen plasma to establish a final state of 50-50 HD in the core, but where a 10 to 15% difference arose in the edge due to turbulent diffusion with a buildup of the hydrogen or the lighter species, which is consistent with our analytic results. So overall, our results can be used to inform the development of these types of scenarios with the integrated modeling frameworks. So in summary, a new isotope mass scaling law has been developed to describe the electron-to-ion mass ratio dependence of the turbulent energy fluxes in both ion-dominated core and electron-dominated edge transport regimes. The electron-to-ion mass ratio dependence arises from the non-adiabatic response associated with the fast electron parallel motion. The non-adiabatic electron drive regulates and strongly destabilizes the turbulence and plays a key role in altering, and in the case of the L-mode edge, reversing naive gyroBohm ion mass scaling toward agreement with experimental trends. The finite electron mass corrections from the non-adiabatic electron drive are generally larger for lighter ions like hydrogen and for higher safety factor, such that while they are generally weak in the ITG core, they tend to dominate the mass scaling in the edge. And finally, for the particle transport, we know that at 50-50 dt, an asymmetry develops between the deuterium and tritium particle fluxes, such that the tritium is better confined than the deuterium for arbitrary turbulence regimes. But equal D and T particle flows can be restored with a slight deviation in the density fraction or density gradient, which can have an impact on the development of solutions for DT isotope ratio control. So more information can be found in our publications listed here or any of the references throughout the presentation. And thank you for your time. And let me know if you have any questions.
Okay, excellent. Thanks, Emily. That was great. Very detailed exposition on the gyrokinetic effects and simulations of isotope effects on transport. So the talk is open for questions or comments. And I have a few, but I'll defer to the audience if they have some. Professor Troy Carter.
Emily, nice talk as always. Interesting to hear the updates too, at least to me, some of the new work that you're doing. This asymmetry in the particle flux is interesting. I'm wondering if that asymmetry could lead to a hollow profile for one of the species. In other words, a situation where you might have a positive density gradient for one and a negative for the other. I ask that because I'm aware of potential instabilities that might arise in that kind of scenario. Do you think that situation might arise and some other modes might develop because of it?
Yeah, I definitely think that that's something that can occur. And that's why we're interested in someone to take this to the next step, which is to do the integrated modeling of what the effect is of these are, what we're talking about here is just basically the particle fluxes, but that's not actually what the density is at a given point in the profile. And for that, you really need the integrated modeling analysis to see whether that has the effects that you're talking about. And that is something that we are currently exploring directly now. That's related to the DT experiments at JET, where it appears that these types of asymmetries might have an impact, particularly on the negative impact on the impurity transport.
Got it. All right, there's lots of students on here. Right? Kyle's here, he has lots of spare time, so maybe you can do that too.
Kyle's doing some great work. Give him some more. Professor Diamond.
That's such a rare formality from you, Dr. Badger. So question is, how, if one tries to understand the result for the isotope trend in the ion heat flux, how can one understand that from the point of view of this kind of time-honored type of calculation that you showed for the particles? In other words, quasi-linear theory and mixing length, right? That's something that everybody understands, and it's very clear, where the bodies are buried, as it were, in that type of analysis. Can you get the result for QI from something like that, and how? Because it's not so dramatically clear how non-adiabatic electrons are going to affect the QI for ITG, except perhaps through the mixing length, which is what I'm curious about.
Right, except that we don't believe that mixing length theory has enough of the information to capture the finite electron to ion mass ratio corrections that are leading to the reversal. So our standpoint is basically that it is a nonlinear effect. And yeah, I totally agree with you that so far we only have this kind of more of a scaling or a hand waving theory based on the electron bounce frequency of what can be causing the reversal for the ion and electron energy fluxes. But like with the particle fluxes, you might note that I had written them very generally in terms of this these factors that depend very heavily on electron dynamics, like the fluctuating potential, gamma itself, and the most importantly, the electron particle flux. So I wasn't really able to say any specific information about that, except based on whether or not we thought the terms were positive or negative or dominant or subdominant, which effects would be more important in saying what the ion fluxes like the D or T would be more important. So I don't, I would say personally that I don't know at this standpoint if it's possible to have a quasi-linear analytic theory for the particle fluxes in the same way. I think that would be a very difficult problem.
Well, it would be interesting, I think, if you could say something about the isotope trend of the scale of the mode, right? Because you know, one would think that the turnover rates for the ITG or the time scales, it's hard to see how they're going to change so much. But the thing that could change is the mode structure. And that, by the way, would be a change in the mixing length, right? Which is a nonlinear effect. It would be interesting because there's a lot of people in the world, as you know, you mentioned Quali-Kiz and all of this out there running quasi-linear models. So it would be interesting to kind of, you know, either to help them or to declare them terminally insane, I think, one way or the other.
Right. And that was one of our, the point you brought up about the quasi-linear numerical models was an initial concern that we had with this work related to Quali-Kiz and TGLF in particular. And that was something that we worked with Gary on. And as I sort of alluded to, but didn't harp on too much in this presentation, a major concern is that there are a lot of numerical models that are using this bounced averaged electron model for basically for their electron physics. And it basically doesn't appear that that's going to be enough to capture these finite electron mass corrections. So that's something that we are working with Gary Stabler on trying to come up with some kind of better ways to incorporate these effects into their quasi-linear models.
Yeah, I was being polite given the audience. I mean, TGLF is in the same boat on this issue, as you surely realize. So.
Okay, yeah, I sort of have a follow-on question, but I see Kyle has one, so I'm gonna let him go first.
Thanks, George. Emily, great talk. So I had a possibly maybe naive question. So at least at DIII-D with our recent isotope campaign, we saw that increasing Q95 decreased the hydrogen heat flux quite substantially. I wanted to ask if there was a comment on, like, based on the theory that you've presented, is there an explanation that's consistent with that observation?
Well, I mean, one of the problems is that decreasing in an experiment, there's never a chance to just decrease one parameter without changing other parameters. And that's one of the reasons why we like to explore this problems like this from a theoretical point of view, because we can in our codes just change one effect and keep everything else exactly scaled to look explicitly at what the one term or type of dynamics is doing. So I would be a little bit suspicious if changing the Q95 didn't also change something else, like particularly something related to the turbulence drive. Like, what is it that exactly changed? And one of the caveats too is that if you're changing Q by too much, you can be downshifting. Like, a lot of times you can downshift the turbulence spectrum, and if you start to become very close to the marginal stability, then the zonal flows that I talked about was really relevant for these kind of L mode regimes where you had a really strong electron turbulence drive. But if you are closer to marginal stability, then effects like the zonal flows might become important and might be driving the isotope scaling for those types of turbulence.
Okay, thank you.
Okay, so I don't see hands at the moment, so I wanted to circle back a little bit to something related to what Pat was asking, but from the perspective of the poor experimentalist who was trying to understand the isotope effect, but looking at plasmas that are fairly similar, but if we're stuck looking at turbulence parameters such as turbulence amplitudes, radial correlation lengths, or mode numbers, or decorrelation times, are we going to see this effect in those parameters? Like, should we expect that the turbulence, something simple like the amplitude, is higher, or maybe something not so obvious like the phase difference between density and potential is shifted, that we might not be able to measure so readily, or correlation lengths or decorrelation times? I'm just trying to think where, we can try to follow this up experimentally and verify or validate or invalidate the ideas.
Right. So I think this particular effect you should be able to see it in any type of measurement that can measure what you're calling the amplitudes or the intensities of the fluctuations. And we had something in one of our earlier papers that was specifically related to the cross phase. And it was that basically that we could show that the mass scaling was directly related to delta phi, and that the ratio of Q over delta phi squared was basically independent of the ion mass. And they were correlated in a way such that if you knew that what the finite end fluctuations were in delta phi, you could basically predict what the scaling would be for the energy flux. So that's indicating that it is basically the strength or of the intensity or the amplitude and not the cross phase that is giving this effect. So I don't think that you would need a complicated measurement like that.
Okay, well, it gives us some hope, but thanks. And I see Pat wave his hand immediately, so probably explaining why I fouled up my question. So go ahead, Pat.
This is partly directed at you too, to make your poor experimentalist even more miserable. If the obvious relevance of this story is to the pre-LH transition edge, right? Mm-hmm. So an obvious question is, if you take this story and you couple it to some simple shear suppression model, right? Can you get the LH transition power thresholds right? You see what I mean? That would be the simplest possible model of the transition, right? You take this kind of drift wave ITG turbulence in the edge regime with the non-adiabatic, strong non-adiabatic component, and use it for, basically use that to compute the relevant gradients and see when the thing tips towards stability. Right, that's an industry that's 30 years old or so. I'm curious, have you looked at that at all?
Yeah, we haven't looked at that side of it. And I think from our point of view, from the theory, what we'd like to explore first is exactly what the isotope scaling is only in the H mode also, and then to consider the L to H transition. And that's a problem that we're currently working on, because I think one of the difficulties with the L to H transition is that a lot of the experiments that I've looked at for the published research, particularly the recent hydrogen data that JET has produced, there's kind of a caveat where the input heating powers aren't really the same. And I think that's kind of making it difficult to interpret the PLH results. So it's almost like you want to separately consider the low mode region and the the low confinement and the high confinement, and then look at what the influences are in the transition between the two. But I mean, I'm sure, as you very well know, that I mean the LH transition is quite a difficult theoretical problem computationally, and we don't really have a lot of good models for exploring the transitory states like that.
Well, the advantage, of course, would be that if you had confidence in a simpler model. I mean, I would just make the comment that this story from the circulating electrons would bring Q into the matter, wouldn't it?
Yes.
It seems unavoidable, and I mean that's something that hasn't been talked about so much in the LH transition problem. So that would be interesting.
Right. Along those matters, one of the experimental trends that we're looking at, or scenarios, is particularly the current ramp ups and ramp downs that will be used for ITER, that I think George yourself have done experiments on D3D related to that.
I can't resist making one comment that just we have looked at hydrogen versus deuterium LH transitions and on D3D, and in fact you do see significant differences in the turbulence characteristics right before the transition. In the very edge, I'm talking like the last 5 or 10% of the minor radius, where everything, you actually see higher amplitudes, from remembering right. This is my Anne of UCSD vintage herself who did this work, but you actually see higher turbulence amplitudes in deuterium in this very edge region. You also see, but you see higher decorrelation rates for hydrogen. So it kind of suggested that you needed more shear to say suppress the turbulence in hydrogen than you did in deuterium. So it went the direction of the LH power threshold. You need more shear, more power flux, something to get the transition. So I haven't quite figured out if that's consistent or not with what you're seeing, but there are some detailed measurements of that particular case. So maybe that would be interesting to look at in the context of your gyrokinetic models a little more carefully. How in this case, amplitudes, mode structure, and decorrelation rates definitely change significantly. So we have a couple of questions. Nils Leithold.
Yeah, thanks for the very nice talk. It was rarely that I, as an junior scientist, can, as an experimentalist, follow theoreticians' talk. So you didn't lose me here. So good job. I had a question. I think it was around slide 30, where you explained the different contributions with the different prefactors C1 and C2, and which differentiates then where the electron mass, finite electron mass effect became important. And sorry if I didn't catch it, but this C parameter, on what does it exactly depend? And based on that, is it actually possible that, for example, in advanced plasma scenarios with current drive in the center, where you get a peaking Q profile in the center and a higher Q in the center, actually possible to also benefit from this effect with a better scaling? Or
right, I think that we so the C factors are very general. They depend on, they basically represent everything that's not the parallel streaming term. So the parallel streaming term is basically where the dominant explicit Q appears, and that's why the Q dependence is so strong in the non-adiabatic part. I mean, here it's given asymptotically as Q squared, but this is just kind of the asymptotic expansion, and presumably it can be a lot stronger than that. But the P here is basically representing all of the other parameters, including basically like the turbulence drives, like the ion and electron temperature and density gradients, and any other rotation or collisions or whatever that might affect the specific level of the turbulence, but not necessarily definitely not including any kind of electron mass ratio effects. So the particular point was just to isolate that the only time you can really see this MI over ME is outside of the C's.
Okay, got it. Thanks.
Hey, Jeff. Is Jeff there? Jeff Cannon?
Yeah, sorry, I'm here. Something just happened to my computer, just as you asked. Okay, I just wanted to comment on Pat's question or comment about, H mode and the LH transition. And it's certainly something we've been looking for around a year. And we see, unfortunately, the simulations that were done for this theory were, I guess they're called ion scale simulations. So they weren't particularly expensive. So we were really able to do, hundreds. But in looking for the LH transition, in the pedestal and in H mode, you're led into multi-scale simulation where the turbulence, the spectrum, instead of just being localized around, K theta rho I of 1 or less, the spectrum extends up, to K theta rho E of, order 1. So they become much more expensive. So it's much more tedious. So, I mean, we're looking for some kind of phase transition between, say, an ion dot. The LH transition is like some solution transition from an ion scale turbulence regime to a multi-scale turbulence regime. So, but so far we're not really successful, and it may take time to really, yeah. Oh, okay, right.
Right. It's basically, we have a huge computational allocation this year to specifically study this problem. We're just not ready to show the results here yet, but looking at what the isotope scaling difference is between when you have just the typical ion scale turbulence versus these really complicated multi-scale regimes. So hopefully we'll know the answer to that by the end of the year.
Before one of us drops dead or something. I think the difference between the left and the right, we think this kind of, we speculate that this is a type of transition that might characterize the L to H transition, but we don't really have any good. It's just suspicion. I guess we don't really have strong evidence for it.
Okay, I'm not seeing other questions now. So I wanted to actually go back a little bit. And so of course the isotope effect is seen broadly. We see it, we've seen it in ohmic and L mode and H mode plasmas. You're focusing here your simulations, I guess, on the edge of an L mode, those are kind of parameters you're looking at here, but it seems to be quite a bit broader than that. So I guess I want to go back, like your graphs showed this transition from kind of the ion gyroBohm expectation to the strong non-adiabatic effect around this row of 0.8, I think it was, in one of your pictures, where there was kind of a crossover. And I'm just wondering, can you highlight, like, what's special about that? Is it just that where Q or collisionalities happen to transition, or is there something else you can kind of say, like there's something magic going on there?
Yeah, it does. I have done parameterizations around this regime to see when I can get it back to gyroBohm scaled, basically, and to get the lower values of fluxes. So it is a combination of Q, but when I say that Q has to be large, we're not talking about, I'm only at 0.9 here. I'm not at like 0.99999 or something. So by large Q, Q is about 3.5, and that's generally when we tend to see this type of transition, because as the scaling shows, it goes at least like Q squared. So it's pretty strong. But it's a combination of Q and the driving gradients being stronger, particularly if the density gradient is stronger or something. And that's related to those C factors that the student previously was asking about. It's basically that prefactor, the C2, which contains the density and the temperature gradients. And you can show that with the combination of the two, if you can increase the driving gradients, then you don't have to make Q as high to get the transition, but you can see the transition, as I showed, even for an ITG type simulation, if you have high enough Q. So it doesn't necessarily require being in a TEM regime, which was, I think, kind of what people were thinking we were saying initially.
Okay, that's very helpful. Maybe help to explain kind of the broad nature of the isotope effect. Okay, any more questions or comments from the audience? Kept people here well past our 1 hour. I think that kind of expresses indirectly the interest in the topic. So why don't we go ahead then and thank our speaker, Emily, virtually or actually. Very nice talk. I think this was great for this audience and very timely too. Of course, it's interesting, for the most part, results that relate directly to experiments we're doing now in D3D. You heard a lot about the hydrogen campaign and of course also JET with DT and as we look towards ITER. So this was great. Pat or George, are there any final conclusions or can we just wrap up here?
I think you can wrap up. Thank you
Okay.
to Emily again.
Yes, great. Thank you very much, Emily. And with that, we'll adjourn. And there is a recording, I think, for those who are interested for that. Thanks very much. Thank you, Emily. Bye.